Today we are looking at putting together pretty much everything that we've learned this semester into helping us graph functions. And before we do that, we're going to talk about concavity and what it means to be concave up or concave down, and how to find where a function is concave up or concave down. So concavity kind of gives us the shape of the graph. And so if we have something that is concave up, it's kind of like a U shape, that parabola. This is concave up. And upside down, this is concave down. Okay, so let's look at this, because a function can be increasing and be concave up, and it could be increasing and be concave down. Vice versa, same thing with decreasing. It can be concave up someplace and it can be concave down in some place. And so if we're increasing, our function could look something like this. And so notice that this is increasing everywhere, but this piece in here, that first piece, as we're coming in from negative infinity to some value, maybe like I'd say about right here, and this is concave down. And this piece in here, as we're increasing, is concave up. This point where we're changing direction, or concavity, not really direction, is called an inflection point. An inflection point is the point where concavity changes. Okay, so let's just look at a picture where something was decreasing, but concave up and concave down in different spots. And so here's something that is decreasing. Notice that this piece, that first piece again, coming in from negative infinity, this is concave down. Where this piece is concave up. The book kind of explains this, and I never really thought about it until I think last semester when I used this book, is that look at how if we look at the tangent line, when we're concave down, any place where I'm putting, where that ruler is, would be the way that my tangent line would be going. So notice that my tangent line, when it's concave down, is always above the curve. And then as I'm moving over here to concave up, notice I'm always below the curve. Okay, I could do the same thing as I was decreasing everywhere with my little ruler over here if I could fix it. So concave down, I'm always above the curve. I move along the line and do my tangent line. And then concave up, I'm always below the curve. Okay, so let's look at how do we find the intervals where we're concave up and concave down, and that point, that inflection point where it's changing direction. This brings us to some tests. The second derivative test. So the first derivative test, it showed us where our function was increasing, decreasing, and that helped us find our local maximum and minimum points. And now the second derivative test, if our function is twice differentiable, if we take the second derivative and we find some interval I where the second derivative is greater than 0, then the graph is going to be concave up on that interval. If we look at the derivative, the second derivative less than 0 on that interval I, then the graph of f over that I is concave down. Concave up, I kind of think of and it's positive, it's a bowl, it holds something. I don't know if that helps or not. Concave down, it's negative. It's less than 0, it can't hold anything. So that helps or not, I don't know. If it does, then you can use it. If not, just lose it. So now let's look at the definition of how to find the inflection point, or what the inflection point is, but I've already said that. So a point, C, f of C, so the x value C, where the graph of the function has a tangent line and where the concavity changes, is called the point of inflection. Okay. So again, C, f of C, and we can find this point where it's changing concavity is either when our second derivative is equal to 0, or when the second derivative fails to exist at some value of C. So to get that point, we're going to plug it back into the original function. Okay, so let's look at this example and use what we just learned. So in this example, it says identify the inflection points and the local maxima and minima of the function graph. Identify the intervals on which the functions are concave up and concave down. Okay, so it gives us a picture. We really don't need that picture. And it doesn't, I mean, I can locate and look at it and tell you where things are, but it wants us to find those exact values. So we need that function. And again, in here we have y is equal to 3/4, all times the quantity x squared minus 1, and that quantity of x squared minus 1 is all raised to the 2/3 power. Okay, so let's look at our derivatives. So looking at this, I have, again, let me just write it here. Y is equal to 3/4, parentheses, x squared minus 1, raised to the 2/3. So we're going to need to take the first derivative. And if I was going to be graphing this, I would find out where, well, let's do it anyways. So let's take the first derivative. So I notice here that we need our chain rule, right? Because we have this parentheses here, raised to the 2/3. So this is our outer function. So taking the derivative, and I would denote that by y prime or dy over dx, dy dx, equals, that coefficient in front is just fine. We're going to leave it alone, 3/4, times, bringing down our power of 2/3 of the inside, x squared minus 1, subtract 1 from our exponent. So 2/3 minus 3/3 is negative 1/3. Can't forget about multiplying by the derivative of the inside. So the derivative of our inside function, which is x squared minus 1, that derivative gives us 2x. So let's rewrite this, but when we take the second, well, let's rewrite this first, and then we'll talk about the second derivative in a second. So we have dy dx. Notice things simplify a little bit. We have a 3 in our numerator and a 3 in our denominator, so those cancel. We're left with 1. We have a 2 here in our numerator. 2 goes into itself once, and a 2 goes into 4 twice. But notice over here, this is strictly multiplication, so I can do this. Some of you were canceling funky. really, really bad on the test, where you have addition in between terms and canceling. Can't do that. So we can cancel that too. So notice that all we have left in our numerator is that x. So this is equal to x all over x squared minus 1, all raised to the negative 1/3 power. So our critical points, this is when our derivative is equal to 0, and this is where our derivative is undefined. And so looking at this, notice that our derivative is equal to 0 when x is 0. So we know we have one at x equals 0. That sets my numerator equal to 0. And then let's look at our denominator. That denominator, x squared minus 1, I notice I can factor that. I'm going to ignore that exponent of negative 1/3, and that negative 1/3, right, should be positive because I brought it down to the denominator. So looking at when the denominator is 0, well, that denominator factors as x minus 1, x plus 1. So x can't be 1 and x can't be negative 1. And that's where it's undefined. So our critical value, we have 1 and negative 1 also. Okay, so we'll put those on the number line and let's start testing to see where it's increasing and decreasing. And actually, you know what? We really don't need to do that, do we, with this picture? Let's use it. They gave it to us. So notice this. We know exactly where it's changing position. Negative 1 at 0 and at 1. So we know that at negative 1, and that value is 0, that we have a min. We also have a min at 1, 0. That maximum value right here is when x is 0. We could figure out what our y value is by plugging it back into our original. So if we go back in here and we look at what y sub 0 is, plugging it back into my original, this is equal to 3/4 all times 0 squared minus 1 in that parentheses raised to the 2/3 power. So this is 3/4. I have a negative 1 raised to the 2/3 power. Well, I can look at this as the cubed root of negative 1 squared. That helps you. So squaring that negative 1 is 1. Cube rooting of 1 is 1. That 1 times that 3/4 is 3/4. So 0 3/4 is our maximum. Okay, so that was just finding our critical values. If we hadn't had that graph, then we would have to see where it was increasing and decreasing by testing our intervals. But this problem gave us our graph, so we're good. Now we want to find out where it's concave up and concave down. And so that is, we need to look at the second derivative, and we want to see where that is equal to 0 and where it's undefined. I'm going to rewrite our derivative with the x squared minus 1 raised to the negative 1/3 power. Instead of down in the denominator, I'd rather use the product rule instead of the quotient rule, but you can use whatever you would like, either one. Okay, so I have y prime is equal to x all times the quantity x squared minus 1, and that's raised to the negative 1/3 power. So taking the second derivative, we're going to need to use the product rule, and within the product rule, we're going to need to use the chain rule. So I'm going to treat x as my first function. Derivative of my first function is 1 times my second function, which is x squared minus 1 raised to the negative 1/3, plus my first function x times the derivative of my second function. Okay, so my second function, I'm going to use the chain rule. So bringing my power down front, negative 1/3 of the inside, which is x squared minus 1. Subtract 1 from our exponent. So negative 1/3 minus 3/3, that gives us a negative 4/3. Times the derivative of the inside. So the derivative of x squared minus 1, that gives us back 2x. Okay, so we need to clean this up to figure out where this is equal to 0. Let's maybe try doing some factoring. That might help us. We could put things down in our denominator and get that as a single fraction. We can, whatever you guys want to do, but we need to get this cleaned up so that we can figure out where this is equal to 0 and undefined. Okay, so first term or grouping, we have this x squared minus 1 raised to the negative 1/3 power. Plus, so right here, I notice actually it's a minus because of that minus or negative 1/3. So minus. Here we have a 2x. Think of this as 1/3 x. So that's going to give us a 2/3 x squared. And we have this x squared minus 1 raised to the negative 4/3 power. Okay, so let's pull out what they share in common. And we're going to pull out the smallest value. And so negative 4/3 is smaller than negative 1/3. Look on the number line, negative 4/3 is to the left. And so I'm going to pull out x squared minus 1 to the negative 4/3 power from both of those terms. So if I pull that out of this first term, we got to figure out what's left. Okay, so if I multiply this and I'm distributing it, remember powered, same base, we add our exponents. So we're thinking to ourselves, negative 4/3 plus what is negative 1/3? Well, negative 4/3 plus 3/3 is negative 1/3. And 3/3 is 1. So what I would have left here, if I pull out a negative 4/3, that would be x squared minus 1 to the first power. Minus, well, I pulled all of this out of here. Right? I pulled that all out. So what I'm left with then is this 2/3 x squared. I technically don't need that parentheses there. I'm going to just drop them. And I can combine like terms inside that bracket. I have an x squared minus a 2/3 x squared. So x squared, if I want to think about this with a common denominator, right, that's going to be a 3/3 x squared. So a 3/3 x squared minus a 2/3 x squared. That gives us a 1/3 x squared minus 1. And let's bring down that x squared minus 1 to the negative 4/3 power into the denominator to make that exponent positive. Just gonna give myself some more room really quick. And so we're going to have this x squared minus 1 to the 4/3 power. That 4/3 power, though, is the same thing as the cubed root of this to the 4th. Okay, so we need to find out when is our double derivative equal to 0. And when is that double derivative undefined? Well, that double derivative is equal to 0. We only have to look at that numerator piece. And so this is when 1/3 x squared minus 1 equals 0. If we add 1 to both sides of our equation, we get that 1/3 x squared equals 1. Multiply both sides by 3, x squared is equal to 3. So x would be plus or minus root 3. And then where is it undefined? Well, that's when our denominator is equal to 0. And so really all we have to worry about, we're looking at when is that x squared minus 1 equal to 0. And if you don't see why, if you think of this as, let's go back to raising it to the 4/3 power. We can use rules here that we can clear our exponent there by raising both sides of our equation to the 3/4 power. So power to power is multiplying. That's why I raised both sides. So 3/4 power, and that gives us an exponent of 1 on that left-hand side, leaving us with the x squared minus 1 equals, well, the 4th root of 0 is 0, and 0 cubed is 0. So we can either factor this and set each factor equal to 0, or we can use the square root method. X squared is equal to 1, take the square root of both sides, x equals plus or minus 1. So I have 4 possibilities that can be my inflection points. I would have to test my values. I would make my number line like I did for my first derivative test, and I would test values into my second derivative to see if it was positive or negative. If it was positive, that tells me it was concave up on that interval. If it was negative at that test value, it's concave down on that interval. But again, I'm given this picture here, and so I don't need to do that. So identify the intervals on which the function are concave up and concave down. Well, looking at this, actually, let's put these on the number line a little bit. And I'm going to grab my picture and put it over here. Okay, so looking at our values here that we just found when the double derivative is equal to 0, smallest to largest on the number line, we have a negative square root of 3, we have a negative 1, we have a 1, and we have a root 3. Okay, so looking at this, so notice that this right here looks like it's concave down. We know that this is the value where it's changing directions. And those were the values we found before, negative 1 and 1. And so we know that it's concave down in this interval. To me, it's hard to see this. Is it concave down or up? Kind of looks like a straight line. So here between -1 and a -√3. So this is where maybe I would go and test it to see, is that positive or -1? Here's √3. And so if we chose a number, let's just do it. Let's choose a number that's smaller than -√3 there. And so smaller than -√3, how about -2? So plugging this into our second derivative, we want to know, is this positive or negative? So we have the double derivative of -2. This is equal to, so again, I don't care what this value is, unless I was actually going to graph it, then no, I don't care. I would need to know what it was in the original to figure out if it was positive, what the point was. But right now I just want to see, is it positive or negative? So 1/3, -2 quantity squared is positive, and that's 4. So it's 4/3 minus 1. I know 4/3 is bigger than 1, so my numerator is positive. This is all over. And so let's look at plugging in -2 in for x here. So same sort of idea that -4 quantity squared is 4, 4 minus 1 is 3. Well, 3 raised to any power, that's going to be positive. So this is greater than 0. And so this is telling me that it's concave up here. And now let's look at between -√3 and -1. How about -1.5? And so plugging this in, let's just see if we have positive or negatives. And so squaring 1.5, -1.5, we get 2.25. Divide that by 3, that's 0.75. 0.75 minus 1, that's a negative number. But the denominator, that negative number, I'm raising it to a 4th power. So that's positive. Actually, I don't know. Anyways, it doesn't, yeah. That anything right there is going to be positive because I'm raising it to the 4th power and then cubing it. So that's going to be positive. So this is less than 0. So this piece is concave down. Okay. Notice about symmetry here. If we notice this is reflected across the y-axis, it's symmetrical. And so kind of from that reasoning, I can say, well, then this has to be concave down and this has to be concave up. So I just wanted to know the intervals. And so let's write it in interval notation. So concave up, we said it's from -∞ to -√3. Union √3 to infinity. And we're concave down from -√3. It's still concave down here. It's just not differentiable. Notice that that's not differentiable there. So I'm going to just put in these to -1, union, -1 to 0, not to 0, to 1. union 1 to root 3. Okay. So that took a while because of part of it is because I'm explaining as I'm teaching and explaining at the same time. But these can take a little while of time to do because there's a lot of different steps that you're putting in together. So let me see if there's any questions.
I have a question.
Yeah.
So when you wrote the interval notation for concave down, could you just do from negative root 3 to negative root 3 to 3 is concave down instead of writing all the union?
Right. So the answer to that question is that we can do that. So let's rewrite it as from negative root 3, comma, root 3. The other thing I noticed just looking at this was that it wants us to find out what those inflection points are. And so the inflection points are the points where it's changing concavity. And so where it's changing concavity is at negative root 3 and at positive root 3. And so to find out what that point is on the graph, you're plugging it back into the original equation. And our original equation that we were given was y is equal to 3/4 parentheses x squared minus 1 all raised to the 2/3 power. Because of symmetry, I noticed that when I look at y of negative root 3, that's going to be the same thing as y of positive root 3. So we only have to look at one of them to know what both of them are. So let's just plug in the positive. So this is equal to 3/4 parentheses. I see an x there. So we're going to square that root 3 minus 1 raised to the 2/3 power. So we have 3/4. Root 3 squared is 3 minus 1 raised to the 2/3. So we have 3/4. We have 3 minus 1. So that is 2. And that 2/3 power, so that's the cubed root of 2 squared. But 2 squared is, I'm going to write it as 4. If it wanted me to give the exact answer, I would leave it like that. If I was graphing this, though, I would not want to leave it like that because that wouldn't tell me much of where that was on the graph. So I would plug it in the calculator and I would get that 3/4 times the cubed root of 4. Gives me approximately, or it actually is, equal to 1.19. So our inflection points this is at negative root 3, comma 1.19 and positive root 3, comma 1.19.
So, to find the points of inflection, you have to take what you found with the second derivative and plug that into the original equation.
Right. So we have to first figure out where it's changing from concavity, concave up and concave down. And we found that by figuring out when our second derivative was equal to 0 and undefined, plugging it into our second derivative, see what was greater than 0 or less than 0. If it was greater than 0, it was concave up. If it was less than 0, it was concave down. And so we saw that there was 2 spots where it was changing. That was that negative root 3. It was going from a concave up to a concave down. And also at positive root 3, where it went from a concave down to a concave up. And so because those are the places where it changed concavity, where it did not change at -1 and 1, these are the inflection points. So -1 and 1 are not inflection points because that's not changing concavity. But to find the points on the graph, we have to take those, which we found from the second derivative, and plug it back into the original equation.
Okay, and you kind of answered the other question I was going to ask, but undefined values can also be inflection points, right? Not just zeros.
Exactly, those undefined values. Well, if it's undefined for the first or second derivative, so same thing as where it's changing direction, increasing and decreasing. It could be where it's undefined, but it has to be defined back in the original function. And in our original function, all those values were defined. If we look at our original function, our domain, because it's the cubed root, and then squared, our domain is all real numbers. And so because they were defined in our original, those could be inflection points or maximum values if we're talking about the first derivative.
Cool, thanks.
You're welcome. Any other questions? So there's another test to test for local maximum and local minimum points, and they use the second derivative test. You can use this if you like. It doesn't always work. Sometimes the test is inconclusive and we would have to go back to that first derivative test to see where our graph is increasing and decreasing to determine if we had a max or a min at a critical point. But let me give you this. I'm gonna make a little more room. Okay, and blow this up. Okay, so our second derivative tests can be used to find our local extrema. So instead of looking at the sign changes of f prime at the critical points, we can sometimes use the following test to determine the presence of and nature of local extrema. Okay, so the second derivative test for local extrema. Suppose f double prime is continuous on an open interval containing x equals c. If we can plug that value back into our second derivative, so it has to be defined there, and we see that the second derivative evaluated at c is less than 0, then it's going to have a maximum at x equals c. And I might have stated that wrong. So the first derivative, this is our critical value. Remember, we find the critical value when the first derivative of c equals 0. So if it's defined at c, first derivative gives us back 0 at c, plug it back into the second derivative test. If it's less than 0, think of it less than 0, concave down, then we know that this value here at x equals c is going to be a maximum. If we found that x equals c was a critical number, it set our first derivative equal to 0. And we plugged it into the second derivative, and the second derivative is greater than 0, then we're going to have a local minimum at x equals c. So this is concave up and concave up. We're going to have a min at c. Well, if you find out that c equals 0 for the first derivative, so critical value, and you plug it back into the second derivative, and you get back 0, you don't get greater than 0 or less than 0, then this test fails. It doesn't tell us anything. We have to go back to the first derivative test. So the function of f may have a local maximum or a local min, or neither at that value. So if you prefer, you can use that this test to find that local max or local min, or you can continue to just use the first derivative test of where it's increasing and decreasing. And if we're graphing it, you might as well just use that first derivative test because you need to see where it's increasing and decreasing anyways. But it's up to you. That test is also, you can use it. Okay, so in here somewhere I put another problem. There we go. And so let's go through and just talk about really quickly graphing procedures for f of x. So going through and putting everything together that we've been learning, here are tips to help you graph our function. And you don't have to do it in these orders in particularly, but we want to look at our function f. It's helpful to test for symmetry, because if we know that it's symmetrical, then we know that it has some, if we have one point, then we know what other points are. So is it symmetrical with that y-axis? Is it symmetrical across the origin? We want to know what our domain of f is. And then we're going to find our first and second derivative of our function. Find the critical points of f, if any, and identify where the function behaviors, identify the function's behavior at each one. Okay, so setting our first derivative equal to 0, setting our first derivative and finding where it's undefined. Those are our critical values, and then we're going to test our behaviors on each interval, increasing or decreasing. So find where the function is increasing and where it's decreasing. I just told you where to do that. Then we're going to look at finding the inflection, points of inflection, if any occur, and determine the concavity of the curve. Okay, so we just talked about inflection. That's where our second derivative was equal to 0 or second derivative was undefined. You're going to test values on each interval and see if the double derivative is greater than 0 or less than 0 to see if it's concave up or concave down on that interval. If we have a rational function, then we may have asymptotes. So we found that vertical asymptotes, those were values which set our denominator equal to 0, but not also our numerator. If it set both, we learned that that was a hole. It could be a removable discontinuity. If it just set the denominator equals to 0, we knew that that was a vertical asymptote. We can use limits as x goes to positive and negative infinity to look at the end behaviors of our graph to see, is it shooting off to positive infinity or negative infinity? Does that mean that there's no absolute max or absolute min in there? Or is there somewhere way that we can see that we'll see that there's a horizontal asymptote? Possibly. Okay, so identify our asymptotes, and then we're going to plot key points such as intercepts and points found above to sketch the curve with any asymptotes that exist. Okay, so doing that, here is a problem to kind of put together and graph using what we just discussed. Okay, so in here, identify coordinates of any local and absolute extreme points and inflection points, graph the function. So y is equal to 4x cubed minus x to the fourth. And this is equal to, if you wanted to factor that, x cubed times 4 minus x. Okay, so I look at this and I notice my domain is all real numbers. Right, we got a polynomial, smooth and continuous. Looking at this, I can take the derivative, and I probably would not factor it to take the derivative because I don't want to use the product rule. And so I can take the first derivative pretty easily because that's just using the general power rule. So 4x cubed, that derivative is 12x squared, minus the derivative of x to the fourth is 4x cubed. We want to find out when this is equal to 0, so this would be helpful. If I factor it, we can pull out a 4x squared, and that would leave me with 3 minus x. So finding where my derivative is equal to 0, setting each factor equal to 0, I see that's when 4x squared is 0 when x is 0, and 3 minus x is 0 when x is 3. So those are my critical values. I want to test on each side into my first derivative to see is it increasing or decreasing. So let's look at a value smaller than 0. So -1 works. If we plug in -1 into the derivative, we want to see, is that going to be a positive or a negative number? So plugging it into this first derivative, -1 quantity squared times 4, that's positive. And then 3 minus a -1, so 3 plus 1, that's also positive. And this is greater than 0. So that tells me that it's increasing on the left of 0. So choose a number now that is between 0 and 3. So how about 1? If we plugged in 1 wherever we see an x, 1 squared is 1 times 4, so that's positive. And so we have a positive, and then 3 minus 1 is also positive. Positive times positive. This is greater than 0. So this is also increasing. And then one more number that we need to test. So let's look at x equals 4. Let's plug it into the first derivative. Well, 4 squared, that's positive. And then three minus 4, that is negative. So this is greater than 0. I'm sorry, this is less than 0. Okay, so we know where it's increasing, we know where it's decreasing. We know that looking at this at x equals 3, we have a local max. If we think about the end behaviors though, notice that we're increasing until we hit 0. We kind of level out a little bit because we got a horizontal tangent line there. Then we're going to be increasing again. My guess is that's also the place it's changing concavity. Then at x equals 3, we change direction. And then we're going to be coming down forever. This is 3. Say that this is 0. And so knowing these end behaviors on my graph, I can tell also that at x equals 3, I'm going to have a absolute, this max is actually an absolute max. And we can figure out what that value is by going back and plugging it into our original function. So y sub 3 is equal to 4 all times. Actually, let's plug it into the factored form. That's going to be a little easier mathematically. So we have 3 cubed all times 4 minus 3. Well, 3 cubed is 27, and then 4 minus 3 is 1. So 27 times 1 is 27. So we have an absolute max at the point 3, 27, and the maximum value is 27. Okay, so now let's look at this. We want to find the second derivative, and that's way we can find the concavity of our graph. And so we have the first derivative, and let's look at the first derivative, not in the factored form. So my first derivative here is equal to 12x squared minus 4x cubed. So let me take the second derivative. And so looking at the derivative of 12x squared, that gives me 24x. Minus, and the derivative of 4x cubed, this gives me 12x squared. said 24x, but I didn't write the x in there. So let me put that in. So we want to find when this is equal to 0. So to me, it's easier if I factor. So let's pull out, they both have a 12x in common. If I pull out a 12x from 24x, I'm left with 2 minus, and if I pull out a 12x from 12x squared, I'm just left with an x. So my double derivative is equal to 0 when x equals 0 and when x equals 2. Okay, so I kind of already graphed this and I'm probably showing, and I don't know if that's my concavity or not, because technically this could be coming up like this. So let's check it. And let's just check it. So let's look at our values that set our second derivative equal to 0. And that's also defined everywhere. So there's no values for that. We're going to test values on the left and the right of these and plugging it into the second derivative. And so if we just want to look at sign values, we can look at that derivative, second derivative factored. So if I look at x equals -1, so we have the double derivative of -1. So 12 times -1, that's a negative number. And then 2 minus a -1, that's 2 plus 1. So that's a positive number. And so negative times positive is less than 0. So that tells me here that this is concave down, which is what I kind of thought was going to happen. And then let's look at x equals 1. So that number is between 0 and 2. So let's put that into our second derivative. And so if we have 12 times 1, that's positive, times 2 minus 1, which is positive. So this is going to be greater than 0. And so if that's greater than 0, then this is concave up. So notice that it's changing here at 0. And so that tells me right here that 0 is an inflection point. And then let's see what's happening on the right-hand side of 2. So if we plug in, let's say x equals 3, well, 3 times this 12 is positive, and 2 minus 3, that's negative. And so this is going to be less than 0. Since it's less than 0, we know it's concave down. And that was at 2. Okay, so we had this concave up until we hit 2. We're going to change direction, and now we're going to be concave down for the rest of the time. And so concave down. From -infinity to 0, union 2 to infinity. And then we have concave up. We saw from 0 to 2. Points of inflection. We have to plug this back into our original function. And so we have the points of inflection at 0 and at x equals 2. So I need to get my original function. My original function was x cubed all times 4 minus x. I'm gonna plug it into this. So if I plug in 0 there, well, 0 times 4 minus 0, that's just 0. And then if we plug in the value of 2, wherever we see an x, we have 2 cubed all times 4 minus 2. So I have 8, 2 cubed is 8, all times 4 minus 2, which is 2, which gives me back 16. So 0, 0, and 2, 16 are our inflection points. Not to scale, but we found those important points. I guess we can find one other important point. That's where this is crossing. I can see that that's going to be crossing when x is 4. So I'm just going to put that, right? Because I can set this equal to 0. 4 minus x is 0 when x is 4. Okay, so see if there's any questions before I stop the video.